steps that involve in the PCM. Okay, so here are the steps that you have to remember. So the first one is sampling. Okay, the second one is quantization, and the third one is encoding. So the sampling process is just the sample of the analog signal will be taken, okay, for a specific time. Okay, this is the sampling process. Okay, and then quantization here. So this one is actually rounding off of the value here, and then encoding is converted the value here into binary number. Okay, we'll go through one by one these three steps here. Okay, for the sampling process, so sampling is the process of taking samples of the analog input signal. Okay, so this is analog input signal, and it will take the samples at a rate of Nyquist sampling frequency, okay, at a specific rate. Okay, most important factor in sampling is the rate at which analog signal is sampled. Okay, so sampling rate is very important in sampling. Okay, so according to Nyquist sampling theorem, it states that for a sample to be reproduced accurately at the receiver, the sampling rate must be sampled at least twice of the highest audio input frequency. Okay, so here are the equations that you have to know. Okay, the sampling rates must be higher or equal than 2 times of the input frequency or modulating frequency FM. Okay, so the minimum sampling rate is equal to 2 times FM. Okay, so the larger the sampling rate, so it is much better. Okay, so consequently, the minimum sampling rate is equal to twice. So this one here. Okay, what happens if the sampling rate is less than 2 times FM? Okay, less than the twice of the highest audio input frequency, what happens? So distortion will occur. Okay, so this distortion is called aliasing or fault over distortion. Okay, so you will go through this in detail during your semester 3 when you learn about the basic communication system. Okay. Alright, so we go to the next step, which is quantization. So quantization is the process of converting an infinite number of amplitude possibilities to a finite number of conditions. So from this figure here, you can see this is the sampling process, okay, in a specific sampling rates. Okay, we have seen about the sampling rate before this. Okay, so when the analog signal, this is the analog signal has been sampled, so it has a specific value here, okay, for each of the sample value here. Okay, so the quantization process is the process of rounding off this value here. For example, we get the value here is 2.1, for example, okay, for example 2.1. So when it goes to the quantization process, so it will be rounded off to 2.0. Okay, for example. Okay, the second one here, the second pulse here, the value here, for example, 4.6. So it will be rounded off to 5 or 4.5. Okay, it depends on the quantization level as well. Okay, so one thing that we have to consider is the quantization level here, okay, which is equal to this equation here. So L is equal to 2 to the power of n. Okay, so n is actually the number of bits per sample. Okay, so the number of quantization levels will depend on the number of bits per sample. Okay, so let's take a look on this one here. So n for this one here is equal to 2 bits. Okay, so the quantization level will be 4. Okay, L is equal to 2 to the power of 2, which is equal to 4. So you can see here it has 4 levels, 1, 2, 3, 4. Okay, so each of the level here has its own code. Okay, so this is where used to code the analog signals. Okay, when we used to code the analog signal. Okay, so for example, when the n here, the value of n here is equal to 3, so the level will be 2 to the power of 3 is equal to 8 levels. Okay, 8 quantization levels. Okay, so the higher the quantization levels, okay, so more accurate will be the digital signal. Okay, which means it will be approximately the same as the analog signal. Okay, when the level is much higher. Okay, now we go to the last step, which is encoding. So encoding is a process where each quantized sample is digitally encoded into n bits code word. Okay, it is related to this equation here actually. L is equal to 2 to the power of n, and this one is just use the same equation. So we just bring n in front. So n is equal to log 2 L. Okay, so the process of encoding is just we want to transfer the value for each of the sample here to a specific code. Okay, so which is the binary number, okay, 1 and 0. Okay, let's take a look on this example here. So this example is also included in your manual, okay, lab manual. Okay, so we have an analog signal here. So this one here is analog signal. Okay, and then we want to convert this analog signal into a digital signal, okay, using PCM. Okay, now the first step is that we have to sample this analog signal, okay, with a specific sampling rates. Okay, the first sample will be here, okay, and then with specific sampling rate, it will be sampled to the second one, third, fourth, fifth, sixth, and seventh. Okay, so the first one, the value for the analog signal for the first sample is 1.3. Okay, the second one is 3.6, 2.3, and so on. Okay, so we go to the next step, which is the quantization process. So as I've told you before, this quantization is just rounding off process. Okay, so you can refer to this table also. Okay, so for example, the value for analog signal is 1.3. Okay, when it goes through the quantization process, it will be rounded off to 1.5. Okay, you can refer to this table here. When the value is 1.3, so it will be within this range, and the quantization level will be 1.5. Okay, so this table is as a reference for you guys to see how is this value is obtained. Okay, and then 3.6, so it is actually between this value here. So for the quantization level, the value will be 3.5. Okay, it will be rounded off to 3.5. Okay, and let's take a look on this one here, minus 2.4. Okay, so it is within this range here, so it is equal to minus 2.5. Okay, after the quantization process, so the value for this quantization level will be converted to the code number. Okay, so for each of the level here has its own code here. Okay, 0 till 7. And for 0, it is 3 bits. 3 bits of the signal. Okay, so for 0, it is 0, 0, 0. And then 1 is equal to 0, 0, 1, 2, 0, 1, 0, 0, 1, 1, and so on. Okay, so when the code number is equal to 5, so you can just refer to this table here, 5, and the PCM code is 101. Okay, so the PCM code will be 101 here. Okay, 7, refer to the table, it is 111, 6, it is 110, and so on. Okay, this is how we obtain the PCM code for this analog signal. Okay, so one thing that we have to consider is the noise consideration, okay, for the PCM system. So there are two major sources of noise. The first one is the channel noise, okay, which is introduced anywhere between the transmitter output and the receiver output. Okay, so which is the medium from the input to the output, there will be a noise. And then the second one is the quantization noise, which is introduced in the transmitter and is carried all the way along to the receiver output. Okay, so what is actually the quantization noise? It is the round-off errors. Okay, remember during the quantization process, we rounded up the value for the analog signal, okay, to the value for the quantization. So there will be an error, okay, when we round it off. So the error of the quantization, okay, QE can be calculated from this equation here, okay, which is quantized sample value minus with input signal. Okay, so if the quantization error we want to get in terms of percentage here, so we just do this equation here. Okay, quantized sample value minus with input signal over with the input signal and then times with 100. Okay, so the maximum quantization error is given by delta V over 2. Okay, delta V is actually the level, okay, the difference of the level. So this one will not be covered in your lab, okay, but it will cover in the next semester in the basic communication system. Alright, so that's all for PCM theory. Thank you.